So that leaves the speaker of the day.
Should I introduce?
No, I will introduce
Oh, okay.
I guess Cecilia has been at the CFA for at least 10 years that I know.
Yeah, I was 5 at the time. I was very, very young. Yeah.
But the best way to describe her actually is as a theoretical physicist turned analyst. The first time I met her, she was working on the solar and stellar dynamos, and then she has worked on machine learning. What's it called? Bayesian neural networks. And currently, she is leading the CFA AstroAI initiative. AstroAI. But very excited to have her here because she's been like the beacon for machine learning at the CFA. So take it away.
Thank you, Vinay, for a very kind introduction. Let me share the screen. Okay, and let me know. Do you see my screen, people online?
Yes.
Try to
Yes.
do this. Oh, hide floating. Okay. Okay, yes, I'm very. Ooh, we have to move these away, right? So you see that, and I don't see my mouse.
Hit the underscore button. Oh.
What?
No.
Oh, I don't know how to do it. Wait, sorry.
Are you okay?
But how do I see the mouse?
Oh, let me see the mouse. It might be on a different screen. So
Okay, let's put you guys here. Okay. All right. Very excited to talk about AstroAI. Always, if you've met me before, you know that that's all I talk lately. So AstroAI is the new initiative. We started officially in November. Actually, in November, we started something called Camel that ended up being a pilot for AstroAI. And AstroAI, what we do in AstroAI is we design and develop machine learning and AI for astronomy, across astronomy. And so why do we need AstroAI? Is because of a few reasons, right? There's all this petabyte revolution era in astronomy that having too much data, it to me is equal to having zero data if you don't have a mechanism to make sense of it. It happens to me with the pictures in my cell phone, but that's another problem. So we need to make sense of all these huge volumes of data. And I do not think as a community we're ready in astronomy to do that right now. So we need to develop methods and models and tools and techniques that are not the traditional ones we've been using so far. But also, I think AstroAI is needed because of all the new discoveries that could happen that are laying there in their current data sets that we just haven't looked at them with this new set of eyes. If you like, with traditional methods, we're not able to see the same things that we can with machine learning, with some machine learning techniques, for example, some patterns. You can find things that you're not expecting with some of these models. So that is another thing. I remember I can tell you stories and stuff. Or
yes,
okay, okay, it's very informal. So I remember that one time I think I was talking with Avi Loeb, and he told me if we had AI 60 years ago, we would have probably found out about gravitational lensing events, because if you do unsupervised clustering, maybe they would have all fallen in a common cluster, and then you look to see what they have in common. So I think there's a lot of things that can be discovered in the existing data sets that we just didn't yet. And so also because in this era of a lot of data coming in, there will be so many transients that right now when there's a transient event, we point all our telescopes, if it's interesting enough, to observe a particular event. But when, with LSST, for example, there will be so many of these that we will have to again, either have a good mechanism to pick up the interesting ones, or we're going to be missing a lot of interesting things. So I think these are just a few reasons why I think we need to have something that is more than each of us doing a bit of machine learning, more centralized things. So the unique thing about AstroAI that I was surprised myself about how it grew and the success and the impact is that we do machine learning and AI, but inspired by science. So we develop models for particular science problems. Right now in the community, it is pretty divided between scientists that, like astronomers, that use machine learning, and some of them very well, and collaborating with computer scientists and statisticians, but for their own research, right? And there's all these other fields where the leaders of these fields know everything about the science, but they do not know machine learning. And so all these questions that might be lying in these data sets, or all these problems that could benefit from some techniques, are there not being attended. So I think that's one of the unique things about us, is that we take projects from scientists that are not doing machine learning, and we build a team that is interdisciplinary. And so another thing that we do that has been proven very successful is that by centralizing these efforts, we're able to retain knowledge. For example, we developed a model that took us months to do. Well, all our projects so far have been student-led. So one of our students, I'll talk about that in a little bit, Ethan Trujillo, developed a model for X-ray binaries, to characterize X-ray binaries. And then we started talking with Mercedes Lopez Morales, who's a leader in exoplanets, about doing a project with her to characterize exoplanet atmospheres. And we thought, we can start from Ethan's model. So there you save months of starting and reinventing the wheel and starting from scratch. And I've seen this problem over and over again. We have developed models for cosmological data, for example, a probe mission concept that we're using mock data to find the redshift of sources and the temperatures. But the data is data cubes, so you have an image, and each pixel has a high resolution spectrum. And then when we work with methane sat, that is a satellite looking at the atmosphere, is the same data and is high resolution spectrum. So we can use almost the same model. So that's why I think it's really important to do this rather than each one developing. Yes,
So
go ahead.
In this particular case, though, wouldn't you, if you're trying to take something that is learned from a cosmological spectrum, apply to a different wavelength region, would you not get misled by, I don't know, maybe the lines being in the wrong place and stuff like that?
I will repeat the question because I think the microphone. So Vinay is pointing out that, if I understand correctly, is asking if you have trained or developed a model for cosmology, then when you use it for the atmosphere, for a different problem, won't you be misled by things that are learned from that domain? Yes, absolutely. But we are reusing the model architecture because of the data structure. And then we're training the model.
Oh, you're retraining.
Yeah, we're retraining. But the most time in these projects is figuring out what model we're going to use and building it up and trying different things in terms of architecture, if it's a neural network, or combining models or different expertise. So you save still a lot of time. You just retrain it, but that's not the biggest part. It's not a large language model or things that you have to train for months. And then another thing why I think AstroAI is unique is because we're at CFA, and CFA is one of, if not the biggest astronomy institute in the world. And so we do this across astronomy, and then we have all the astronomers there, a lot of astronomers and leaders in their field, and a lot of very interesting projects. And so another reason that is good to be at CFA is because of the Boston area, because we have the astronomy expertise in the CFA, but we also have the AI, machine learning, and statistics expertise in Boston area. So what we do is we bring all that to the science, And I think that's what has been a need. So we started, this is a little bit of history, no statistics. I apologize for that. Actually, I apologize that there won't be a lot of statistics in my talk.
No worry, we have plenty of statistics here.
Okay, good.
But I do have a quick question.
Yeah.
When you talk about advantage, is there any advantage at being a CFA because it has particular powerful computational resources? Is that
No, well, it has no,
Oh.
the is the science and the scientists.
Okay.
So unlike many other efforts, we do have a scientist lead the project, lead meaning supervise the science part of the project. We don't take the project, develop our tools, and because that has been done and it doesn't work. Either the computer scientist goes too far with their models, but is missing something that,
Okay.
you know, some domain knowledge, or, you know, or you don't have the sophisticated models if you do it just with the scientist, the astronomers. So we bring them together, but we work together all the time. And that's one of the things. But in one of the projects I'm going to talk about with the exoplanets, at one point where there's a lot of modeling and stuff, and then one of the things that was key was Mercedes, who's the astrophysicist, said, okay, but if you have this and that, then you have the radius of the planet. You don't have to learn that. You just like, you need both. You need all the expertise. That's my, at least, what I learned is you need all of the experts in the room once a week to get a project to really be solid from all the different perspectives.
Well, we're certainly very glad to hear that. I mean, this is like, in our terms, it's called a highly principled AI. Right? We have this notion called a highly principled data science, meaning you have to have statistical principle data, the scientist, the direct input and competition efficient. And it sounds like this is exactly why it's works. So perfect. Thank you.
Yes, you're welcome. So this is just a little bit of history. We started in November. We were just a few people that get together. This four in pink are the experts I had nearby in the CFA, and we started this with 13 students, no, with 9 students, but half of them were in the computer science side of things, and the other half were astronomers. So this was a true interdisciplinary collaboration with 4. Right, yeah. Somebody said, what is a turn on and off button? I look at it and I think of a computer, but you're right. But yeah, that's what it
Get a star. I see.
Yeah, there's stars. See?
God, that would be hard for a statistician. What do we do? A p-value or something.
You'll have to find that. That's why you're not here. We need statistician, but I just didn't figure out what the symbol would be.
Yeah.
No. Okay, so we started with 4 projects. And we call this Center for Critical Machine Learning, CAML. So let me tell you about a couple of projects. So for example, how we do things. This is a project that was for, I briefly mentioned it, for X-ray binaries. This is a system of a compact object or a black hole that you're seeing there with an accretion disk. This is an illustration. This is obvious for any astronomer. I'm sorry about that, but I want to make sure because not everybody's an astronomer. So just in case, this is an illustration of a system that is a binary system. So it has 2 objects. One is a compact object that is a black hole or a neutron star that has accreting material around it. And the other one is the star, which material is being accreted by the black hole. And so this accretion gets this dynamic gets the gas very hot and it emits in X-rays. So we can see these in X-rays and they're called X-ray binaries. So, but really what you see when you don't have that illustration, but you have the data is a spectrum like the one on the left here. And if you see enough of these spectrums, you can characterize the system. But what you're interested in is really to know the temperature, the mass, the spin, the physical parameters of the system, right? So to do that, you need an expert like Jack Steiner, and it will probably 10,000 of these spectra. That's what Jack tells me. I trust him. That takes Jack 24 hours of work to characterize a system like that. So that's where Ethan came in. So we started doing this with Jack. We would co-supervise students. I would supervise the machine learning side of things and he'll supervise the science. Because again, we're in CFA, we want to take advantage of all the science, but I don't need to know all the science. I cannot know all the science. So we always have the science person that in this case is Jack. And Ethan was was a Southampton student at the moment. And so he built a model, an autoencoder, and I don't know if everybody knows this, or I'll explain what an autoencoder is. Okay, so an autoencoder is a model, is a neural network. Here, all the symbols that you see, and I cannot point because the mouse is not there, but all the symbols you see are layers. A layer has neurons, but neurons not the neurons in the brain, just a representation that has a mathematical operation, a nonlinear mathematical operation. And so you give this model a data set, like the one on the left, spectrum, and the goal of an autoencoder, which is a particular kind of neural network, is to reproduce at the end, to give you as an output the same thing, as close to the original as possible. The key here is that it has to go through a code, through a bottleneck. So if you pass this data, if not, it will be straightforward, right? Just give me what I give you. But if you have to reduce it dimensionally enough, and then you can reproduce the same or as close as you want, which I know for statisticians is not enough, but imagine that you get the parts of the data that you think are important, the shape, for example, then it means you have captured the important information in that code, so that you have reduced you have a better way of storing that information. And that is just how do you say, compressing information. But the key thing here is that if you could make that code have the physical parameters of the system, which is tricky, because autoencoders are known, and machine learning in general is known for having this black box problem. Like, okay, you have the code, but what does that mean? It's not going to be in a basis or in any way that typically that you can interpret it. But Ethan was able to make sure that the code had the physical parameters that we need from the system.
So can I just think about the code is essentially is in a statistical term is like a low dimension model.
Yes.
And these parameters are actually later actually has meanings as a physical
Exactly.
index that.
Exactly.
Okay.
And the very, very simple example, I would say much less sophisticated than the concept you just gave, is imagine you have a lot of points on a line, and you give that as an input, X and Y of each point. And then in the code, you could imagine that there's going to be a version or a different representation, maybe of the slope and the coordinates. Yes, so you're just capturing the important information by forcing it to be lower dimensional. But the key thing here, the big achievement, was that Ethan was able to do this while making sure those are the physical parameters. The way he did that was, first, he trained the decoder. So you go from the low dimensionality to making the spectrum. And we were able to do that because we have a model for that is called XPEC, that you can make synthetic data from parameters. So we use synthetic data for this. And so once we had learned how to do this, we also, as a byproduct, we have, how do you call this? An emulator for XPEC that is expensive computationally. So now we have an emulator and we can train end to end.
So when you, what's the role that why do you need neurons or any sort of non-linearity to go from physical parameters to XPEC? And we know how to do that, right?
Linearly.
Yeah. I mean, you generate a theoretical model and
with XPEC, we can do it. Yeah, right. XPEC takes a very long time, and then you're learning that with a neural network, with a generative model, and is instantaneous.
If you start from, I mean, if you start from a known model, evaluating model is fraction.
Right. No, but it's not a known model. You're trying.
So then I didn't quite understand what you did with the training.
It's not a known model, right? I'm not an expert on XPEC, you guys are, but you have the X-ray binary, right? And then you have to choose some parameter space for models. And then you do the fitting with XPEC, but it's not fast, at least not what he was doing. I would need Jack to describe that.
Oh, you're actually doing a fit.
Yeah.
So I think you have this spectra, and you were showing the components of the spectrum. The first spectrum, and there is like 5 different elements of physical objects, components, which go into the spectrum, and each of them is related to the emission process. And in some cases, you have just the black body, which is very simple, but you can also hot corona, which causes condensation, and then there is absorption, there are emission lines. So all these separated components are present, but you don't know the levels at which they contribute to the observed spectrum, and that's what you fit. Typically, when you have one source,
No.
you fit
no.
that, right?
No,
So that's kind of in this physical parameters, because it depends on the mass, accretion rate, density of the material which absorbs.
That requires that going from a known, no, in fact, I mean, in statistics terms, it's like conditional on the parameters. Generating the spectrum is straightforward. That you're not just doing that, you're generating a spectrum and fitting it again.
I think you can generate the samples of spectra, and then it would be allowed, right? And then you can, based on these numbers, like 10,000, let's say, which was given, you can select the set, which is for this particular.
Okay, so
right?
let me tell you what I think. So I'm probably people are missing this discussion. Vinay is asking, why do we need that a nonlinear neural network to go from physical parameters to spectrum when we know how to do that? It's not my kind of science. I'm not an expert. I think so. What I know we did was we tried to do this part with XSpec directly, right? But we do need this part because we want the first part. We need the encoder to get the physical parameters. So we do need the second part. But the second part was taking forever when we were doing it in real time. If you want to train a neural network, you need something really fast to go from physical parameters to spectra. And that's why we needed the emulator. And now the details of how fast you're saying XSpec is versus what I was hearing from Ethan and we were trying things is that it was not fast enough.
I'm missing something here. That's
I guess the reason you do the emulator is for computational purpose,
Yes,
because you can generate
Exactly.
things much faster.
exactly.
Even you may sacrifice a little bit because it's not exact thing, but if it's good enough.
Exactly.
it's what you
Yeah.
do, Okay.
But
It's not a
you-
simulator,
but-
you actually know the thing, but you build it in emulator, you reduce.
It's an
it.
emulator,
Yeah.
right? And it's actually, you can do it as close as you want to the real, because it's synthetic data. So if you're not happy with the performance, you just include more synthetic data and train more. You can get as close as you want. But yeah, anyway, so the only importance here for the second part is to then be able to train end to end. And when you train end to end, you need that to be very quick. So that's why we did it. Okay, so anyway, he trained first the decoder, so going from the parameters to the synthetic spectra, and then we froze the decoder and trained the encoder. And then we did transfer learning with real data. And so that was cool. And I know that this is not good enough for you to show you how well we can reproduce the data, because it's not a statistical measure, but in the paper, I have the paper in the back of the screen. If you want, I can look into that. There's some tables with how we measure how well it does, but it does very well. This is just a visual way of seeing how well it reproduces an input spectrum, which means you have extracted the physical parameters well enough to reproduce something so closely.
So the blue dots are the original data, and
Yes.
the orange brown one is what you reconstructed.
Yes.
And I see, that is just a residual, I guess.
Mhm.
That difference you're seeing that. I see. By the way, want to make sure that people online, can you guys hear well? If you have any questions?
Can you see the chat? Because
Yeah,
since I don't have one. Okay,
Yeah, if you want any question, please.
okay.
Yeah, we should probably mention, they can stop and ask questions anytime.
Yes,
Yeah, just feel
please.
free to unmute yourself. I see that there's a new.
Oh,
thing.
there's a hand up, Monica has a question.
Yeah.
But also there's a chat has two.
Those are two questions.
Yeah, go ahead, Monica.
Yeah, so I guess my question sort of follows up on Vinay's question in that, you said that the reason you need to do the decoder is because you want to do it fast. But if the model is, if it is expensive to run the simulations or whatever you call them, the XSpec for your range of parameters, what if you don't have your whatever your training set span enough parameter space? That is, it doesn't explore. Then what will happen to your will it find some? Is it able to go to parameter space outside your training set?
No, well, we don't try that. Typically, these kind of methods do not work out of distribution, but expect is that. So I said that we do this because it has to be fast, but as Vinay says, it is fast enough for generating spectra that then we can train on. It's just not fast enough to do it in each iteration, in each epoch if we're training a model. So we did have enough synthetic spectra. It was not a problem to have spectra to generate, to train the decoder. And then I don't think we had a lot of issues with exploring the parameter space either. So we just expand the parameter space that we needed to. So yeah, I agree that it's a potential issue, but we did not have this issue in this project in particular. But it's typically something good to keep in mind. Does that answer your
I guess
question?
I'm just wondering, is there an advantage to doing this over, say, some kind of Bayesian model? If XSpec is fast enough to explore the parameter space in some, can't you just use some kind of inference model to do it?
Vinay can answer that.
MCMC
But you have to
kind of.
speak louder, move closer.
No,
I guess.
I'll just say that, yes, I mean, we do have Bayesian methods to do that. For example, Monte Carlo, MCMC-based method. You just have to run it for a very long time, and I don't think there is each individual model evaluation takes a small time, but you run it for 50,000 times.
Yeah. So yeah, you can do that's the best thing you can do. But this is the objective here is almost the opposite, is to do this quickly. But then one thing we found that this is useful for is you have a lot of data, you do this, and then you start your MCMC from a good guess of parameters. No, it's not complex.
You pick different. You always start from different points and try to make sure. So that just so 150,000 evaluations.
Okay, we can discuss that further, but also you can then use XSpec from this initial value. This takes, just let me tell you that what took Jack 24 hours takes this model less than a second to perform like this. So you can make it perform as good as you want at the expense of, okay, it will take a few seconds instead. And then you have a really good starting, like you have all your spectra with a good enough kind of a first order approximation, at least, right? You have temperature, you have mass. It's better than having all the spectra without any fit. At least you start with something.
So what about uncertainties on this parameter?
Yes. No, I know, and I know this audience. No, definitely that's always a concern. So that's why we think this is good to have a first idea. We are not going to just trust this, but it does perform, like we tested enough that we know how well it performs typically. But it's not a Bayesian, model. So we do not.
So what does that mean? You know how well it performs typically? Would you be able to give some typical error bars then for your parameters?
Well, like typically what you do is you have a test set and you know how the model performs in your test set. That's what I mean. That doesn't mean we have an error bar. We can tell you how well it performed in a test set. you could think of that as an error
Okay,
bar, but
okay.
not in particular for each fit, we cannot.
But do you have a measure? How do you measure the?
Well, you compare it with, well, we use what Jack had data that was fitted and classified and analyzed with the traditional methods. So we use that as
But you know, and given the residuals here, right, you could have a way to evaluate how well it does.
yeah. Right, and that's what we use to train it. Like, that's the statistics, simplest statistics is what we use to train it to say, okay, let's get to this point. But then that's in the space of the spectra, right? But if you want the error bars in the temperature or the mass of physical parameters, is a different story. But we do have, you know, an idea of performance from a test set. But again, it's not a model that will give you error bars.
One comment.
I'd like to go.
Say something. Oh, wait, so hang on, we have just a quick comment. Can you say something about the difference between what you're doing in ChatGPT? Because there's a bunch of comments in ChatGPT that's going off, that's talking about.
What?
The comments in the chat. There are comments about ChatGPT.
In the
So
chat,
that-
they're saying ChatGPT can do this.
Or no, they're
No.
saying difficulties, problems with ChatGPT.
Yeah, no, then maybe I could just say a word or two. It's an anecdote about an experience I had with ChatGPT, and I'm not sure to what extent it applies to AI in general, but it was sobering to me. And I think the lesson is it's a good system for collecting together a bunch of data and trying to make connections that may or may not be real. On the one side, you could say this is an indictment of it being a horrible thing because it invents things that don't exist. On the other hand, you could say, well, it's being creative, and it's saying, in my example, it's saying Michael Frayn should have written a play about Kepler, and maybe he should have done that, or you know, so it can find things that could exist even though they don't exist. And I guess the question is there any danger of that happening in the systems that you're talking about?
I think it's model dependent. You're talking about ChatGPT is a language model, a large language model. It uses transformers, is a generative model, is very different from this. And yes, I agree. We're thinking about training a language model on astronomical data, and we're thinking about doing research on having a reliable model trained on scientific data that has no hallucinations. There's a lot of work in that direction, but that's a different kind of model. And even though we're called AstroAI, there's AI and there's machine learning. And this is more machine learning, what I'm talking about right now. And I don't think here, even though part of this, an autoencoder is not per se a generative model, part of it could be considered a generative model, but not in the same way as with language. It's not a predictor of the next word or what could happen. So it's much less prone to have, there are no hallucinations. Yeah, it can just perform badly, but then you would know that if you have a test set that reflects the whole parameter space, you should pick that up. Does that answer your question?
Well, yeah, but let me try to focus, if I could take another minute, on a related question. I guess I could preface it with, I've seen over the march of time that started with the concept of data mining, and then along came machine learning, and then along came deep learning, and then along came artificial intelligence. And each one, I think, promised to be something deeper and better. But in that whole sequence, there's the notion that, sure, it's great to solve a problem that you already know what you're trying to do. It's not going to invent a new problem, which is 90% of science. If you if you know you want to identify zip codes written by hand on envelopes, it gives you a good solution, but it's not learning at all. You're not learning anything new. And I guess my question is, have any of these systems gone beyond that sort of my naive critical remembering of what things used to be? Are there systems that truly learn, that can go beyond what's in the training data, for example, and invent new things that are real and not invent new things that are not real?
Yes, there's a whole field of it that is symbolic regression, and that is about learning equations from systems. I guess there's two different criticisms here that I feel that they're very separate. One is, if it can be creative, it can hallucinate, but if it's not creative, then it doesn't learn. I think there's different ways of seeing this. One of them is just a tool that I don't expect this machine learning model that I'm showing here to be intelligent or to be someone that I can ask it questions about science, but just a tool that is sometimes more flexible than traditional tools. Just like if you wanted to do science before this, you probably would have no issue with using traditional fitting techniques, saying I have data and I want to figure out what model represents that data. And for that, you had to use methods like this one. This is not so different. It's just a mathematical function that we are fitting. And it's just a more complicated one, and that we're fitting it with more freedom. That's all this is. So I don't see that it not being intelligent, if that's what you were pointing to, is an issue. It's just a tool that is more flexible than others. This is all that is. Then about general intelligence, I truly hope we don't get there anytime soon. So I'm not seeing that as a failure. I think that, and then for discovering new things, I do think these tools can help discover new things. And one of the examples is the one I gave about gravitational waves. If you do unsupervised clustering, if you let things cluster by similarities in a higher dimensional space that you can make sense of, then the system is not intelligent to go and tell you, okay, this is the physics, let's quantize gravity. But you go and you say, why are these being clustered together if I don't see anything from the things I know, that they don't have anything in common from the things we know? What do they have in common? And then that can lead you to new discoveries. Does that answer your question?
Sure. I agree. And there was some work at Stanford a while ago, and maybe it's similar to what you're talking about. It was some work on using machine learning, and I guess they even called it deep learning, to essentially model gravitational lensing systems. And it was actually able to solve problems that were not part of the training data, which I thought was kind of amazing. They were configurations of the lensing system, for example, multiple point masses as opposed to a single point mass, which was in the training data. So that's the only thing that I ever saw that impressed me, that these systems were actually learning something. I'd like to stay away from the word intelligence because nobody knows what that is, but learning, you kind of know what that's supposed to be. And I think there is promise that these systems can do it, but like you say, we need to avoid hallucination. I think that's a great term, which I hadn't heard before. And if I could just one more tangent, maybe a more practical question. Okay, these are sort of black boxes. They're not total black boxes because I'm sure you have lots of tools for looking inside them and so on. But to some extent, I would guess sometimes they get used as black boxes. I guess my question is, do you think that the kind of barrier is too strong a word, but the wall between the astronomer and the statistician is being made more transparent or less transparent by the use of these tools? Is that working together? There are problems where this astronomer tosses a problem over the fence and the statistician picks it up on the other side and doesn't really fully understand the science and goes off and does something wrong, or vice versa. I'm sure that never happens at Harvard, but it could happen somewhere.
We can toss back, you know.
It's a tennis match, yeah.
So do you think this kind of new approach that you're presenting here is improving that situation or making it worse?
It depends. It depends who you ask, I think, and it could go both ways. I think the biggest impediment is the geographical separation between the CFA and the main campus. But being more serious, I've been thinking about this because there's been a lot of new hires that are shared between the statistics department and astronomy because of the boom in machine learning. Because for better or worse, now people are doing more, addressing more problems. Like people are very interested in astronomy, in machine learning, while maybe they were in astrostatistics, but not with this boom, or I don't know, something happened and got trendy. And so that
that's exactly the solution, is to young people to be trained in both sides.
Right,
of that
right.
fence. Yeah.
So I think, yeah, Josh Spiegel, for example, was hired half appointment in Toronto, half by the statistics department and half by the astronomy department. And now one of the AstroAI people that works with us is going to a faculty position in the statistics department in the UK, but he's interested in continuing working in astronomy. So I think that barrier is getting more fluent, hopefully, because we really need statisticians for these things.
So someday there might be Department of Astrostat, just like Department of Statistics. Why not? Right? But who knows? You know, it could happen. Depends on my question.
Diab has his hand up.
Yes, go ahead. Yep.
So I want to drag us back into the muck just a bit. So when I think of machine learning models, I just, as you phrased it, they're just another way of fitting. And in a way, they're very blind fitters. They just don't really care about much of the, the physics of the model. So when you talked about creating an emulator for XSpec, so I'm familiar with the concept in some of the bigger fitting packages out there, like Dakota, which comes out of Sandia, where you can provide proxy models which are faster but a little coarser, but they allow you to approach, the part of your, the solution space faster, and then they switch over to the more detailed models. So I'm trying to understand what sort of criteria you created for the emulator so that you knew what areas it was. I assume it's a coarser version of XSpec, which just has a limited idea of parameter space, but I don't understand why it's, you can run XSpec models, they don't have to fit, they can just generate stuff. So I don't understand the details of your emulator, how it was implemented, but how do you ensure that your emulator is accurate, and how do you determine which sorts of sub parameter spaces you're just essentially going to average over in order to get you the speed? I mean, it seems like there's a whole field of just what goes into creating the emulator. Because that seems to me.
What is the last part of your question? I missed that part, that the average. I missed that part. I missed you there.
Well, your emulator cannot explore all the parameter space of your fundamental model, because otherwise it would be just as slow. So you have to make compromises. So what are the criteria you draw up in order to understand what those compromises are? Because that emulator is the source of truth for your entire model, right? You depend upon its accuracy in order to be able to translate from your inputs to your outputs. So how do you establish the criteria for the emulator so that you can trust what the emulator is doing, and also to give people who are poking at this from the outside some sort of confidence that your emulator is really doing a good job?
I would have to look in the paper exactly what the parameter space, or I can follow up on that. What we did, maybe I'm missing the question, but what we did was we used data that we trusted because it was labeled in a way, right? We had the temperature, we had the mass and the spin, and we used that data to train the emulator in the kind of systems that we were looking at. So we were doing X-ray binaries of stellar mass black holes. And I have to say, I trusted Jack Steiner here, who's the expert on that science, to tell me, okay, we need to go through this range in temperatures, this range in masses, this range in spins. Well, spin is easy because it goes just from -1 to 1. So we had a training set and a test set that was across the parameter space, just like you have to always do it as best practice. Yes, Vinay wants to say something.
No, maybe, forget the supermassive black hole model, but suppose you just had a regression straight line model. How would you build an emulator for that?
Well, you write a linear equation, right? Right, and then you just evaluate it. Now, how do I know that in between 2 points in a linear approximation, there isn't like a lot of an oscillation? No, we don't know, but we don't know that with traditional methods either when we fit something.
No, I mean, what, as Dia asked, what sort of constraints would you put on your emulator to go from slope and intercept to a data set?
What do you mean, what kind of constraints?
That's
I don't understand the question. I think you have a data set that is aligned on a line, right?
Yeah.
You build a little neural network, which is ridiculous because it's a linear problem, but let's say we do it. And then you just tell it, give me the Y for this X, and it will give you whatever. And then you tell it, no, that's wrong, go down, go up. And eventually you'll learn the slope and the ordinate. What are the constraints? I don't understand.
But you could put in some smoothness penalization in.
Oh yeah,
You could
regularization. Yeah.
do that to make the faster instead of
Right.
have to learn lots of data. I think that's what they meant, like.
Oh, okay. So that is
And that's why you call it an
matter of-
emulator, right? You're calling it an emulator because it's not the real thing, right? It's not running a billion different runs of X spec. You're choosing a model which is faster. So you've made a trade-off. So
yes.
I'm not asking for the particulars of this particular work. I'm thinking about in general, as you did this work, did you come upon, I mean, is this a field which is so specific to a certain project that you can't come up with some generalization of best practices? Or is this somewhere where you could say, we came up with these approaches and these tools to determine whether so that we could check along each step what we were getting was correct, and we could take these same approaches and apply them to different problems.
Yes, I think I would step back for a second on that and say that I don't think that by doing an emulator, you're compromising on the real deal always. So let me put an example. If you run a simulation, a numerical simulation for, general relativity magnetohydrodynamics, you know all the laws that take place there, all the physical laws. And yet you don't know what the output would be. But I am not convinced that you cannot learn that. It's just like statistical mechanics from fundamental physics. I do not think that you're going to do worse by doing it faster. It's just a different way of learning. If you can learn the optimization, if you don't have to do the numerical simulation in the same way, it doesn't mean that you're leaving some of these laws behind.
But
I mean, obviously, you're not sure you're imposing them, but if you can compare and you see that the performance is consistently good in every step, for example, then that would give me a peace of mind. And then there's ways of interpreting, right? And saying, why is this? What is it paying attention to? And sometimes even getting equations like symbolic regression for the answer that you get to the problem. If that makes sense.
I guess part of the question is, I think probably one good example is, say, data compression, right? Image compression. You can compress lots of data to human eyes when they recover the picture. It's still pretty good. But I think the question is, what are the criteria here? Because, for example, human inspect pictures, hey, that's good enough. But of course, there's things lost. But you don't just care about it. I guess the question was, is there some, if I might understand the question is like, what are these criteria you have viewed to make the judgment and say, well, that's obviously there are some trade-off there. I mean, you are just saying the trade-off might be very, very minor, or maybe even sometimes these trade-off maybe even advising, because I don't want the noises.
You don't want the noise.
Like the human's eye does not really distinguish noises anyway. Why would I need that? So it's not even a trade-off, in that sense. I think that probably the question was like, what are the practical guidelines you learn from these problems that can be transferred to some other problems where you probably obviously have a good judgment what is good and what is bad, but is there some general?
I think that would be great to develop. I think that would be like a good avenue to take for maybe statisticians to have some kind of guidance like that. I don't know how to make that general. What we do typically is we make sure that we're within the tolerance that we have decided for the particular project based on the physics.
So you have lots of experience there. Your team has lots of kind of a tuning experience. Then say, hey,
yes, and then we just from the scientists we can get, okay, this is a good enough, right? This is if the differences that we're seeing is smaller than the noise, for example, we can be confident that that's good enough for us. It depends good enough for who. And again, I know this audience is not going to be easily convinced that something can just be good enough without a very strict procedure. And I agree. And that's why we need statisticians. I do not have an answer to that.
But the other aspect you mentioned, if I understand correctly, that you're in a situation, you're actually building an emulator for synthetic data. Therefore,
Yes,
you're
exactly.
in a better situation because you can just keep generating synthetic data. So you don't actually have to, you potentially, of course, that training itself is a lot of computation, but so potentially you're in a situation less than some other situation, you need to do more regularization because you don't have additional data to help you.
Right.
Without, but you all seems can always generate the more.
Yeah,
right?
you can
Do
generate
more
it
training.
as good as you want. Yeah, exactly.
Okay, so that's an interesting situation.
Yeah, we did that for many different problems for stellar characterization. Whenever we have a problem like stellar characterization, you have stellar evolution models that are really good, but it's very expensive to try to retrieve the mass and age of a star from the stellar evolution. Is like a inverse problem. And so we just train a Bayesian neural network to learn how to give you the right answer. It takes a lot of training at the beginning, but then it's immediate. So
it's a one-time cost because generate the synthetic data themselves have a cost. But that's a one-time cost.
Exactly.
And once you have this and you want to use the emulator, go on to do
right.
That's
not only you're saving computation, but also you're saving storage. These are just weight and biases. So you don't have to have all the stellar evolution tracks and do the typical thing that
what kind of saving are we talking about in terms of magnitude, order of magnitude?
It depends on the problem, and I don't remember, but it's very small to store any neural network of the sizes that we're doing, of any size. Pretty much it's just numbers, right? And so evolutionary tracks are bigger than what I can put in GitHub, definitely. And a neural network is not.
Just to she solved the Paul Baines problem. That's what she's talking about.
Oh, you mean that CMD?
The CMD. Yes.
CMD problem. Okay.
What?
It's something that we worked on, and it's a massively complicated likelihood space, as you know.
Yeah,
that seems a good work. Otherwise, you're reading the table, right? I remember the likelihood it was completely funny shape. Yeah, I see.
And machine learning would be a much better approach to a problem like that.
So has that been tried?
She's on the,
I don't know what you're Stelnet?
yeah, you've done that, right?
Cellular evolution?
Modeling.
Yeah. Oh, I don't know if I have it here, but I can show. Yeah, we can talk more about it. And there's someone working on that actively right now. This is interesting. I think someone had a question or a comment.
Oh, no.
No. Ah, sorry. Maybe you moved on it.
There is a question from the chat. Where does unsupervised learning enter the picture? Or SOMs? I don't know what SOMs are. And the light part of AstroAI is from Jackson.
Self-organizing.
Support?
Self-organizing maps.
Oh, self-organized.
Yeah, I didn't get to any of that yet. Let me think. We have like 37 projects. But I'm just only telling. It's 1:30 and I have a meeting at 2.
Don't worry, we have, just keep going. That's what happened.
I do have a meeting at 2 though.
Okay.
There's many projects, and in many of them we're doing unsupervised learning. Like we're doing at least we're doing unsupervised clustering for many things. For example, one of the projects is an AGN project that we want to see from a huge amount of data how things cluster, and to see if we're really using the lines that we think are informative, because those were derived in the 90s using PCA, and we want to see if we find something new. We are using that for other, but let me go a little bit ahead on this, because this was just the first one to show that then we started from this for another project, and the other one is a lot. You're gonna be much more
Well,
happy
you
about
can
the
always
other
do
one.
it next time. You're always welcome to
Maybe.
come back.
Maybe,
Next
yeah.
time you-
Okay.
That's how we run this thing. It's a very.
That sounds good.
Just get a conversation going.
So anyway, Ethan is writing this paper and is the third of this series of X-ray binaries, and yeah, I was very gladly surprised that this went also quickly and so good. I think there's a lot of low-hanging fruit, really. This was needed to be done. The next thing was then Mayel Obin came as an intern for the summer, and we started working on this project that I mentioned with Mercedes Lopez Morales, who's an exoplanet giant. Although she's not a giant, she's a small person, but she's a giant in the field. To characterize exoplanet atmospheres, which is a very hot topic and very interesting, from Webb. And it's a challenging problem because the spectra we have from observations is low resolution, and we want to detect very small signals and biomarkers. And so we included Ethan, and this is one of the things that the way we do things is we thought, okay, the autoencoder that Ethan built, because he has this mechanism of being able to guarantee that the code has the physical parameters, then that is a good start for this, because this is also low resolution spectra, and we also need physical parameters. So maybe we start from there. We do a similar process than we did. We start by the coder. And so we build a team. This is one example of how we do these things. So we talk with Mercedes. Mercedes has this cool project. We have this model, and so we bring in Ethan. We have a student, Mayel, that is going to lead the project, and then we bring in the AI experts and also the AstroAI and i5. Some people are i5, people that are in between that speaks both languages. And we brought the spectroscopist in the room as well, because this problem has a spectroscopic component. Well, anyway, all the expertise, and because we have a lot of expertise at CFA as well, is what I was talking about. So this, and Mayel led this work with this whole team. So we always have an AI or computer science supervisor and a science supervisor and everyone in between. It would be good to have a statistician as well, now that I think about it. So we use the same model that Ethan had built, but okay, again, we trained it on different data, right? We wanted to know from the spectra of exoplanet atmospheres. And for the non-astronomers, the idea here is an exoplanet transits in front of the star that is the host star. So the exoplanet orbits a star and it goes in front of the star. And if you compare the light that comes from the star itself and the star with the planet in front, the differences are due to the light going through the atmosphere of that planet, if the planet has an atmosphere. So you try to figure out from those absorption lines, what are the elements in the atmosphere of the planet? And you get very low resolution spectra. Yeah.
One question also related to the question before, I guess. And how do you deal with the instrument response in this case?
Yeah, that's another
I mean,
issue.
like a finite, I mean, you have finite width of a line, and I guess in general you would like to move that back. Just to get like better line separation and all these things. So is this currently taken into account, or do you just say like, okay, it's just like a parametric description of the overall shape?
We don't take it into account to begin with. So we do go from let me get a little bit further and I'll tell you, but this was particular it ended up being for Ariel, which is one of the missions. And then we have to include all the noise and everything. This is more, I would like to talk to you though.
Yeah, I'll send you an email.
Okay, perfect. Thank you for joining. Yeah, sorry it's taking so long. Okay, so we thought, I'll get back to, and if I don't answer your question, let me know. So we said, okay, let's start from Ethan's model, but train on this new data. And what we're starting with this, the Ariel Data Challenge came out, which is the European Space Agency released this challenge asking for the AI community for some help, because Ariel is a mission that is going to go up, be launched in 2029, that will observe thousands of or a thousand, I think, exoplanet atmospheres, and they want a good way of retrieving the physical, the composition, the chemical composition of these atmospheres. So we thought, why not? We're going to do it for web, but let's start with the challenge. So this is the idea. A real team has a way to do a forward model. So if they know the radius, the temperature of the planet, and they just consider a few molecules, right? 5 molecules. If they have these parameters, they have a forward model of atmospheric model to get the synthetic spectrum. They have that. What they want is the inverse, but they can do that. You could do that with MCMC. They do nested sampling because it's faster. And so when you have the spectrum, this is in a very naive way, and I apologize to the statisticians, what you're really doing is you're taking different versions of this input, different values for these input parameters, and getting the synthetic spectrum and comparing and seeing which ones are compatible with this particular spectrum. That's kind of the exercise you do, but it's very expensive. And so they get posterior probability distribution on each of the parameters. They say, okay, the temperature is around this with this much, like these are the ranges of temperatures with these probabilities, and this is the abundance of CO2 and all these posterior probability distributions. That is what they wanted, but they wanted a fast version of their model. So that's what the challenge was about. And the way to score the projects was going to be, well, it was the Kolmogorov-Smirnov test, which is on the cumulative probability. So what you're seeing here tells you how many samples, what is the probability of a value, let's say the x-axis could be an abundancy or a temperature or the things that you're trying to predict. What is the probability that that value is below -2, then 0, then 2? So that's what you're seeing there. And they're comparing the real one that they got with their method to the one you get with your model. And the score is, the biggest difference that you find there is the opposite of the score. So the biggest difference is the penalization. So if you do very bad in one point, it's the same as doing bad everywhere, pretty much. But that is only taking into account the marginal. So this is going to be for each parameter, right? Temperature and radius, and they're all an atmosphere, a spectrum that has water or CO2 is not going to be compatible with. It's going to matter. It could be like this much of this one and this much of that one. But it will depend on each other. So there's cross correlations here that they're not evaluating us on. So this is only the marginals. So it's not a good science model if you do a model that is doing just good on that. But that was the way. I mean, I'm not criticizing. It's hard to find a good metric to evaluate. So we started with the autoencoder similarly to Ethan. And actually, it did pretty well. If you see, we could reproduce the spectra pretty well. Typically, it's a typical spectra, and those are one of the parameters that we're trying to predict versus the true value. So it's pretty much a diagonal. We did very well with all of the predicted parameters, but that was not what we wanted. We didn't want deterministic answer. We wanted a probabilistic answer. We wanted posterior probability distributions. We did not, and that was the case not only for the challenge, right? With Mercedes, she said, I don't want one spectra as an answer, one spectrum. I want to know what part of the parameter space I should be considering and then look at it more closely. But I want to know definitely this does not have water, or it doesn't have more than 20% water, or something like that. So that was a good model, but not good enough for this task. So the next step was using normalizing flows, which is a way of going from a simple distribution, or the one you want, but for example, a simple distribution, to a arbitrarily complicated distribution by a set of transformations that are functions. So you can reverse that, right? If you learn how to go from a Gaussian to that posterior probability distribution, or the other way around, you can reverse it and go from a prior to the real posterior probability distribution. Now, how do you learn that? Well, you take some functions, and then you have to fit the parameters to know what are the functions that are going to be this set of transformations that will take you to the right posterior probability distribution. And we learn that with a neural network. The neural network will give you the parameters for the functions to get from the prior to the posterior. And so we did that. I don't know, but yeah, okay. So the input is the spectra, of course. And we have the output because we have the result of the nested sampling. So we have the posterior probability distributions, and so we train on that. And so here are the two models. On the right is the one that won the challenge. So Mael won the challenge over 293 teams. Because what he did was a trick. He said, okay, they're gonna evaluate us on the marginals, then let's do a normalizing flow per parameter. And then we can do as well as we want. So he did that. But that's not the best model for science, obviously. So he also did the other one, the complete normalizing flow. That did very well as well. So now he's writing one of the ECML proceeding on this. Yes.
What this means, the right one, is that he used multitask learning. He predicted all the tasks using different neural networks?
No, he actually just trained one per parameter. And then when you get the spectrum, you say, okay, you use one for the posterior probability of the radius, one for the posterior. It's not like a mixture of experts. It's not that you use them all and then you combine them. No, it's just much more simple. It's just each normalizing flow was doing a different task, but that is the task. It's not that then you combine them. Right? One was to predict one thing, one was to predict the other. So each posterior probability distribution was its own thing and not taking into account the other parameters at all.
But the inputs all of them were in an input of just one neural node, right?
All of the input, yeah. Wait, you're asking if all of the inputs.
Oh yeah, I see it.
So we did this for each parameter.
Got it.
Okay. But then he did it all together. Yes.
Was there any issue with using the multivariate Kolmogorov of distance? So you mentioned they were only considering margins.
Yeah.
Was there any issue with using the joint distribution?
Is the challenge that the challenge was going to score our results based on the marginals. Yes, on the margins.
As you mentioned, the joint would be better for sciences.
Exactly.
So why?
Oh, I don't know why. I don't know. I think it's harder. Yeah, I don't know how you would do it. Well, it would be just a higher dimensional, or yeah, you could do it, but I don't know the reason. Yeah. But so Mael did both and won the challenge, and everyone is happy. So, okay, that was just an example to show you that kind of what we do. We do these things that the first project was more deterministic, this was probabilistic. We like to keep the knowledge and reuse it. Even in this case, it was not the final model, but many times it is transferable. But we're doing like 37 projects right now. So these are just 2 of them, but we're interested in many different things. So talk to us if you're interested. We are still defining the partners who are submitting an NSF proposal for these AI centers call. And this is just a brief, yes.
So instead of the normal layering flow, if you considered using the variational autoencoder, because this would have been like the straightforward modification of the model that you had before.
Yes, and actually we tried that. And why didn't it work? It's much harder in my experience, and I don't remember the details of what happened when he tried it. But if you do a variational autoencoder and then you use the KL divergence, in my experience, at least with training the Stelnet that you were talking about, is, and I think is a known problem, is that you underestimate systematically the uncertainties, and it's really hard to get the right procedures with that. Okay, so this is just a description of how we grew from November to Jan. So we started in November, and I expected we'll have maybe in a year double the projects and the members, but it really truly exploded. And we're now, I think, at the point that we have 10 papers, if you count the ones submitted, in just a very small amount of time. And we're going now for the NSF. There's a call for AI centers with focus on astronomy. Oh, there's a whole other project I was going to talk about, but I have a meeting at 2. There's no time. Okay. Yeah, we're doing a lot of work with the Event Horizon Telescope as well. We can talk about these variational and conditional autoencoders. Yeah, next time. I don't know. Anyway, here I did have some statistics. So anyway, yeah, okay, so I'm gonna leave it there and take any more questions, but I'm sorry I didn't get to show many projects, but
that's very typical for this group. We never yeah, so absolutely compact, and so they want to inspire some students to even, join the project here.
yes, we're always looking for students that are interested in.
I can tell you that it's not a successful CHASC talk unless the speaker rushes through the last few slides.
Yeah, so maybe you can put it on the whole screen so we can see the people
Yes.
online to see if there are any questions,
No.
comments. Yeah, they're all here. Yeah.
Okay, so I think, yes, you have a talk at Taliban meeting at 2
Yeah,
o'clock.
Yeah.
How to get back to the meeting at 2
Okay.
o'clock.
All right. Okay. Well, thank you so much.
Thank you
Thanks
for having
everyone.
me. This is
There,
really
we will, to be continued
To be
literally. And next Wednesday, no, sorry. Yeah, next Wednesday we'll have another talk.
Is it here, by the way?
Yeah, it's always here. Yeah.